So welcome everyone. We're continuing implementing match expressions today for the Draco compiler. If you've seen the stream last time, you know that the plan is to get something like this working for the compiler, where we have a match clause in which we have match arms, which are essentially cases in like a switch statement or in a switch expression. We expect patterns on the left, and we assign them values or code blocks, and we optionally allow guard clauses with the if keyword to be appended after the matched pattern. The plan is to desugar it into something like this along if-else-if chains, which is not optimal or ideal. We don't have any pattern matching algorithms or exhaustiveness checking algorithms planned yet. This will just make do for now. We are planning to make this usable for types as well, just like in C#, in both switch statements and in switch expressions. And you can optionally bind it to a name, though we are not entirely sure about the syntax. So we are not including this in the stream. Also, I've noticed that there is a small bug in this snippet, so let me fix that. Now, what we've done last time is that we've parsed this match clause. We introduced the new keyword that we needed, the new kind of syntax node, or rather syntax nodes, and we have implemented two kinds of patterns for now: literals like numeric literals. We're not allowing strings yet, and we have implemented the discard or any pattern, which is the underscore for now. We have also added syntax for the entire match expression, the match arm, the optional guard clause, and so on. If you navigate into the compiler, which is this window, and if you open up this syntax XML, you can see that we have introduced the concept of a pattern syntax, where we have two kinds of pattern syntaxes as for now, literals and discard patterns. And we have also introduced match expressions, which is this. If you've seen our syntax tree, you know that we store every single token. We don't throw away anything at this stage yet. And here's the match arm with the optional guard clause, which is defined here as the if keyword, parentheses, and the condition in between. So, what's next on our list is going to be binding, which is the first stage of our semantic checking. We do symbol resolution and type checking there in sort of two stages. First, we convert the syntax tree into a sort of untyped tree or untyped nodes. At this stage, we're just simplifying the tree a little, and we're also collecting type constraints. And once that's done, we solve those constraints and figure out the type of everything. And from that, we can actually go to a bound node form. So we can construct the final bound tree. And this is the same thing that the Roslyn compiler does. When it finishes binding, it produces a bound tree. So that's why the process is called binding. And what we want to do is that for all arms of the match, we want to make sure that the matched expression that we pass in the parentheses can be handled by the patterns on the left. And we want to make sure that if the match expression returns a type, for example, here you can see we always construct string, but in every case here we essentially construct strings, but we want to make sure that they have some common compatible type that the match expression can result in, which is very similar to our if-else expressions, where we want to make sure that both branches result in the same value, same kind of value, essentially. Then we would have flow analysis left, which again, unfortunately, we'll probably do off-stream because it's a bit more complicated, and we need a new kind of analysis process that is probably very boring and very lengthy to work out. And finally, we have lowering, which is not actually that complicated, fortunately. We can do that on stream. For last time, we have written a small snippet, which is this one. You can see that our language server is not very happy about it currently, because I have not recompiled it since we implemented parsing, so it's a bunch of syntax errors. But this is a very basic example. We just want to match on the value 1, so we should have 1 as our result, 1 as a string as the result of this match expression. If we try to compile it, my compiler is set up to be working directly from Visual Studio. You can see that we're actually failing at the binding stage, and this is because the match expression syntax is not handled, it's not being bound to anything. So in terms of binding, what we'll have to do is define the new kinds of untyped nodes that the tree will have, the new kinds of bound nodes that we will have, and apply all the constraints. Hopefully we won't need any new kinds of constraints, but we will definitely need new kinds of untyped and bound nodes. So I would say let's open up the untyped and bound nodes in the compiler. They are both defined in this XML format. It's kind of the same as Roslyn. We are generating a lot of things like rewriters, visitors, transformation methods that makes our life simpler. And as you can see, for untyped nodes, we have 3 kinds of abstract nodes. We have an untyped statement, an untyped expression, and an untyped L value, and I believe that we're going to need an untyped pattern. I think that we have statements grouped, expressions grouped, so I think I'll just scroll to the bottom and open up a new of this block that I've introduced with this comment. And let's just start. So we will have 2 kinds of patterns since we introduced the discard and a literal pattern. I think we can just define both of them. So I don't remember if I called it a discard or any. It's a discard pattern, so we're gonna have an untyped discard pattern, and the base is going to be untyped pattern. And this can stay empty. I don't think that we will need anything in here for now. And we're going to define an untyped literal pattern. And the base is going to be the same. So if you do compiler development actively, this is sort of like the AST, what most people call the AST. It might be a little bit even more high level because it stores symbols, no names are present anymore. And the untyped tree is sort of the awkward in-between stage where we don't know anything yet. We know some types, we do not know some other types, we don't know if certain symbols exist. So this is the awkward in between stage for collecting, but also simplifying, and in the meantime collecting all the constraints for the type system. And then once that's solved, we actually get the nice bound nodes that is much better to work with. So for literals, I'm just going to take a peek at what the literal expressions store. Okay, so it's storing the value and it's storing the type. Now, I think that we are going to need types for patterns, as patterns will, I believe, will only be used to match things that are expressions with types. We have some expressions that do not necessarily have a type. An example would be a member access, for example, system, or rather just the name system is just a namespace. It's not an actual type, so it has no type in itself, but it looks like an expression, and it is handled like an expression. This is why you will see sometimes that in expressions we have two properties, a type and type required. Type required just asserts that expression must have a type, and type in itself is an optional property. But for patterns, I believe that type is always required. And for discard patterns, I believe that we need to infer it from the rest. And for literal patterns, we can just infer directly from the value, just like we do with literal expressions for now, as our literal type inference is not that sophisticated yet. So let's roll with this for now, and we will also model match expressions, which is going to be in the expression bunch, and I think that syntax wise I put it under if expression because it's very similar. Yep, so we can do the same. We'll just define untyped match expressions. And it's going to have, well, not a condition, but we called it, in syntax wise, I think we called it matched value, so we're going to call it the same. And we won't have, we won't really have then and else cases here. We're going to have like a list of patterns, guards, and assigned values. So essentially match arms. I think we're going to create a new kind of node for that. I wonder if we have an example of that anywhere where we don't derive from the base from the main base types. Maybe strings. Yeah, okay. So this is just going to be an untyped node. And the match arm is going to contain sorry, three things. One is the pattern, which is going to be an untyped pattern. Then it's going to contain optionally the guard. And it's going to be nullable since it's an optional member. And we're going to also have the value of this match arm, which is going to be an untyped expression, and that one is required. So with that, I think that a match arm is basically done. We don't need anything more fancy. And what we're going to do is we're going to change this then to something like arms. I wonder how I called it in the syntax node. match arms. Let's just go with that because arms in itself sounds weird. And because we're in XML, we're going to use these awkward escape sequences for generics. And with that, I believe that the untyped nodes should be complete. I don't think we need anything else for now. And while we're here, we could also just copy this and paste it into the bound nodes, because it's going to be very similar. Now, you might wonder why it's not one thing instead of two then. Well, it's quite complex, but the short version is I have not found a way to merge them yet. So what we are doing currently is that we're going to just manually copy paste what's the same. There are things that are divergent in the bound tree and the untyped tree, so it's not all duplicates, but there's definitely a huge overlap. Oh, I see I got some spam in the Twitch chat, so I'm going to delete that. Sorry about that if anyone saw it. I think that the Twitch detection thingy actually caught it and didn't publish it. Okay, and I think we have one thing left, which is the pattern, making that oh, I think I copied a bit too much here. I think I brought over the while expression. Okay, so let's declare a new kind of abstract node called a bound pattern. I'm just going to create a create a new block here for patterns, and for now we're just going to copy what we had. So I really can't type or navigate with my keyboard today. And these are going to be bound. Now, there might be one future where the difference between bound and untyped nodes will be more significant, and this is because there's a possibility that once we will differentiate types that could be potentially type variables versus types that are properly known, or I don't know, in like Prolog terminology you would say that it's a ground value because there are no variables in there. So I'm giving it the benefit of the doubt and keeping the two structures here as long as it makes sense and as long as we're not committed to merging them or changing something significantly. So let's see in the bound nodes, and both are derived from bound pattern. Okay, let's see the change set that we did so far. I don't wanna miss anything. So for untyped nodes, we have defined the new untyped pattern, and we defined an untyped match expression and the match arm, and we have two patterns. Okay, as for bound nodes, it's the same deal. And I think I've rewritten everything to refer to the bound nodes. So let's see if the compiler is happy about the new kind of nodes. I think it won't be because there is no overridable type property yet, and this is because that's declared in code. Because we didn't want to like elaborately model everything in XML, so sometimes we just accept that we define some types partially. This is not it. it's in the bound tree and in the untyped tree. So if you look at untyped node, you see that a bunch of properties are defined here in this partial manner. So this is the same thing that we will need to do with patterns. And I believe that L values, what do they do? Oh, they just declare their types as abstract to make it required. That makes sense. That's what we are going to do. I have no idea why this ordering is for L values. This doesn't really make sense. The abstract one should be at the top, just like with everything else. So quick reordering there. Okay, and I believe the same should be done for the bound nodes. And here it's actually the first one, the bound L value. So we don't specify the abstract again, because that's actually specified by XML. Okay, we compile. So let's commit that we've written the nodes. And let's continue with the binding process. So if we run it again, we will see that we have not handled the match expression syntax yet. So we're just going to write a handler method for it. We're going to shove it pretty low, just above the helper methods. I believe this is a binder for generics, yep, so we can just shove it under it. And we always call the syntax parameter just syntax, not actually what's being passed in. And we should get stuck here now. Okay, here we should be binding the each pattern, or rather each arm. Which involves binding the pattern, the guard optionally, and the value. And we of course need to infer that all the patterns have the same type as the passed-in value, and that there is a common value that the right-hand sides evaluate to. So just a bit more visually, if we go back to the examples, we need to make sure that all patterns have some common type, and that they match this passed-in expression type. And we also need to make sure that these types on the right-hand side have some common type that can be used as the type of what this match expression evaluates to. So let's start that. The first thing is that we can bind the passed-in value. Very simple, just bind that portion. And with that, we already have an untyped expression for the matched value. And next we should bind the arms. Which we'll do in just a second. Actually, there's nothing else that we can bind currently, so let's do it right away. We just need to define that patterns can be bound by these binder objects. So if you look at binder, we have a partial implementation for each kind of node that you can bind. We have one for expressions, L values, statements, and even labels. And we don't have one for patterns yet. So what I'm going to do is create one called binder untyped pattern. And I believe that it's just a top level method. Yep, I'm going to copy it for the documentation. We're the correct one, okay. So binds the new syntax node to an untyped pattern. I generally program like this. I usually never implement anything first. I just start writing this skeleton and throw an argument out of range exception or like an auto-implemented exception depending on the situation. And as I'm progressing and going further, I start filling it in. I believe many of us do it this way. I love coding this way because I don't have to do like a depth first kind of programming style where I just implement this method which needs this method and jumping all around. I'll just write the wireframe and then start filling what's left. So let's start binding the arms, which will obviously need an immutable array builder. Because we need to store each arm. And well, binding each arm is going to be pretty simple. The pattern is just going to be a binding again, binding a pattern which we just declared. We're going to pass in the constraints and the diagnostics. If there's a guard clause, we need to bind the guard condition. The guard clause is not null, we can just take the clause and extract the condition from it and bind that, just like a regular expression. And finally, we can just bind the value of the arm. And that should be it. With that, we have a bound arm. And with that, we should have everything to create, almost everything to create a match expression. The only thing we're missing is a type, which I'm going to leave to do here. And one thing I want to check is what's our naming convention here. Do we prefix them with untyped or anything? But it doesn't look like we do. So this is almost the entire process. We're just missing the type constraints. So again, we need to make sure that all the patterns match the matched values type. So let's actually do that. After we have bound the pattern, we can just add a new constraint. And I think it's called assignable. And we need to be able to assign I need to remember what the ordering of the parameters is. So the target type is what we assign to, and that's going to be the patterns type. And what we're assigning is the matched values type rather, and we are requiring it to have a type. And now it needs to pass in the constraint locator, or the syntax node that originates this constraint. If you watch the for each expression stream, you will notice that we have completely reworked the solver's way to resolve location info. So now we can just pass in the syntax node, and I think what I'm going to do is pass in the ARM syntaxes pattern as the location here. And with that, the type system has the constraint, it will evaluate it, and it will report it if this constraint has failed. Now the other thing we need to do is have a common type constraint for the value, so we can pass in the common type here. What we're going to do is create a new immutable array. So let's see what the parameterization is for this constraint. There's a common type constraint that we have, and we expect a common type, and we expect the immutable array of all the alternative types. So that's going to work. We're just going to create something like value types. And we're just going to store the type symbol in it. And once the value is being bound, we can just have its type. Of course, we require it to have a type. And finally, here we can say that we allocate a type variable for the common type. And we finally can say that there needs to exist some common type within this type, where every value is essentially compatible with that type that we have collected from the right side of the match arms. And the locator for this is going to be the entire match expression syntax. And with that, we have resolved the type of the match expression, hopefully. Now I have no idea if what we wrote will work. Let's try to run it. I think we will now have to fail in the pattern binding process because we haven't implemented a single binder for patterns, indeed. So what we can do is fill out the first kind of pattern binder which is going to be, what's the syntax type here? It's a literal pattern syntax, so let's fill it out. What I'm going to do is I'm going to hop over to the expression binding and find the literal binder here, because we have a utility to find the type of a literal. Again, we're not too sophisticated with literal typing yet. We're planning to be a bit smarter about it, but not for now. So we just have a methodic binder facts that literally matches over the value that is being associated with the token, and if it's an integer, we are going to get the integer type. If it's a boolean, we'll get a boolean type, and so on and so forth. So for now, this will just work, and I think we have another kind of pattern that we haven't covered yet, which is going to be the discard pattern, I believe. Yep. So let's write the binder for that. Now, I think that this is going to be a bit harder to bind because patterns require a value, and I'm not entirely sure what to assign as the type. Because let me just show you. We really need a type for the discard pattern as of now. I am not 100% sure what to assign. I believe we could just do something cheeky for now and do like an unreachable or even like an error type, because it really doesn't matter. So it could be something like the bottom type, and it should be fine. Let's do that, which means that we can actually just return a singleton here, I believe. I don't know if we do that anywhere. Let's take a look, because there might be a good reason we wouldn't do that. So if we look into the untyped nodes, I'm sure there are some singleton nodes here. Yep. There is no operation statement. We use that for importing. Well, what about units, expressions? We do have a default for that, and we use it quite a bit. Okay, well, let's not do that for now. We can do that later. But we can just get rid of the type for the discard pattern in the XML. We can just override it directly in the nodes here. We can say something like we could use the never type just to not confuse it with with any other type. I know it's cheeky, but it's honestly fine for now. I don't want to create a type variable. Well, what we could have done is that we just assign them the expression type, so that would be true like bidirectional inference. I'm not sure if we're benefiting anything from that. Since there's no information from this side, I think assigning the never type here is just going to be fine. Now we just need to pass in the syntax, which is going to be just syntax itself. I think with that the untyped binding process is done. Let's check it. Okay, so we are past the untyped process. The type checker has run, and I wonder if we have any diagnostics here. We have 3 of them, which is not fun. Undefined reference to num. Did we mess up anything here? Of course. Let's do this, because I believe the original sample was very faulty. And we don't need console here because we have already imported system console. So let's try again. I just want to see if we have failed with anything during type checking here. Nope, it doesn't seem like it. It looks like we have successfully completed that. So that's wonderful. Let's continue. So this is going to be the method that takes the untyped node with all the type info and inferred things that has completed just before, and we're going to create the final bound node from it, which is equivalent to the Roslin bound nodes. I think we can just shove it here, otherwise. And what we are going to do is first we're just going to throw an not implemented exception. And let's see that what we've got here in this match expression. So we have 4 arms, which is correct. And we have 4 sorry, I just wanted to look at the matched value, which is an untyped local, and it is an int 32, that's correct. And let's look at like the 3rd arm, which is a guard, a relational expression, that's correct. And we have a discard pattern, also correct. This is the syntax, alright, and the value is inferred to be a string. Now let's see what the match expression itself got evaluated to. It must return a string, which is correct. Okay. So now what we need to do is we need to be able to bind patterns. Let me quickly find where we'll do that. I think we need a bound pattern version of these files. Something like this, and I'm just going to take this version. And this is going to be typing a pattern, not an expression. with that, we should have all the top-level binder methods. So let's continue binding the match expression. So first off, what you can do is bind the matched value. Well, we are calling it typing at this time at this stage. After that, we can just go and type the arms. We're going to need an immutable array builder again. Currently, the patterns are not interesting enough to have anything significant in the typing and binding processes. Later, when we are going to bind things like, we are going to have patterns like the structuring or even just referring types, we're going to have more significant things that we're going to do there. The conversion to bound nodes is usually very robotic. As you can see, oops, we forgot to change the type of this. It's supposed to be a bound pattern. So as you can see, it's very automatic to turn the untyped node into a bound node, so we might want to automate that at some point. I am not sure. We also might want to factor this out into a new function, but I'm really not sure about that because, for example, for the untyped version, does a bit more. If you look here, we have values that are referenced outside the loop and such. So, well, let's rename this from value types to arm value types. That just make more sense. Okay, and I believe that we are at the stage where we can just construct a new bound match expression. Okay, let's see if we fail anywhere. Yep, we didn't type any patterns yet, and we need to handle 2 literals and discard patterns. Pass in the constraints. Well, it's not very important to pass in the constraints for a literal binding, but we're going to pass it on for more complex typings later. And this is just a pattern we follow that we pass in literally everything for all of the cases. And we're going to have a untyped discard pattern as well. Just need to fill these out. Now, if I recall correctly, we didn't remove the type property from the discard pattern here. Yep. So let's quickly do that and modify the bound node as well. To have the same type. For now, we're just going to use the bottom type. And we can finally use the new constructor that has one less parameter. So we can just do bound discard pattern, and we just need to pass in the syntax. As for the literal pattern, we're just going to do a very simple conversion. I think this should be very similar to how we type a literal expression. Exactly, okay. But here it's essentially, for patterns it's always required to have a type, so we don't have two kinds of properties for an optional and a required type like we have for expressions. Now let's say where we get with this. And I believe that we should fail at code gen. Okay, that's wonderful. And we're failing at code generation because we have not lowered this construct and nothing's handling it, so we're not emitting proper code for this. So let's commit what we have, which is binding down 4 match expressions. And we're essentially at the last stage that's worthy of streaming, which is taking this form and lowering it into this form. So we're going from this high-level construct into a bunch of if-else-if nodes, and even that is going to be lowered by the compiler a bit more. So let's just close everything and concentrate on the tree rewrite process. The lowering can be found here, and we have 3 stages for lowering currently. We have the closure rewriters. Now we don't have actual closures, but we factor out nested functions and we make them top-level functions. We have the local rewriter, which does the bulk of rewriting high-level things into lower-level things. And then we have the sequence point injector, which is only interesting for debug builds. Now this is the thing that makes the debugger navigation actually nice. This injects the proper breakpoints, or rather sequence points, into the tree. Now let's look at local rewriter. Just for a few samples, we rewrite variadic methods into array construction. I'm trying to find some nice ones. Okay, so if expressions are being lowered into conditional gotos, the conditional gotos in this form have a separate node. we don't even have if expression codegen, because we just implement this. We also lower while expressions into labels and conditional gotos. We lower for each loops into while loops that gets lowered into conditional gotos again. We lower chained relational expressions. So in the same vein, we're going to lower match expressions into the form that you could see here into this else if chain. So what I usually do is I find a nice place to put it. Maybe put it under a while or right under if, maybe, because it's also a control flow expression, that's not a loop. And what I usually start here is that I write the rewrite process here as a very high level notation, where I have the original form and what we lower into. So that's what I'm going to do here. So this might be a decent small compact example. So let's see what we rewrite this into. So what we do is that first we need to, if you look at this node, we evaluate the matched value and store it in a temporary. This is to stop double evaluation of that expression, because if, for example, this matched expression is an expression that has side effects and we copy paste it into these equality checks here, you would have this side effect applied multiple times, and we obviously don't want that. Do we have notes about that anywhere else? I just want to check. Nope. Okay. So let's continue. And now we have this chain of if-else ifs. Now the unique thing here is that matches pattern 1 is something that is being compiled from the pattern. So the rewriter would take the pattern here and the matched expression and would generate some expression that checks if that expression matches that given pattern. So this is going to be slightly different what the rewriter has done so far. We're going to use PMP here, not the expression directly. So this is the plan, and because we want this in as one bound node, we need to wrap this into a block. Okay, let's first then evaluate the matched value. First we need to lower it, of course. I think that we have a node dot accept here somewhere that we can use. So we will do matched value dot accept. And we also have a utility to store a temporary value like this. Now the method itself is not complicated. If we peek into it, it does a bunch of optimizations. If we are matching a literal, for example, we are just not bothering doing anything. We know that that doesn't have side effects for sure, so we're not allocating a temporary for it. Otherwise, we actually create a synthesized local, which is a local variable that's constructed by the compiler, and we give the user the way to reference to it, which is a local expression, and we also give the user the assignment that they can put into the lowered code to actually give this symbol its value during runtime. So let's continue. We have the temporary value, and now we have to go through each arm. And we need to compile each pattern into its respective form, and we need to be able to match this temporary value, whatever it is. So I think that what we're going to do is have something like well, maybe not compile pattern, that sounds a bit too low level. Construct pattern to match arm.pattern, and we're going to pass in the temporaries reference. So tmp.reference is actually how we reference that value. And we're going to wind that into this condition, but first let's actually generate this method, and I'm going to shove it below all the expression handlers, and this is going to create a bound expression, and throwing the not implemented is totally fine by me for now. And so we have the pattern matcher expression. Do we have the parameterization? Right, well, this is going to be an expression. Well, this is going to be matched value. So we have the expression that tries to match the given pattern. Now we need the guard, which is going to be arm dot accept, and this, and we're going to, well, not arm dot accept, but arm dot guard dot accept this, and we're going to cast that to bound expression. And otherwise I would do something like true. Oh, we have a... Oh, we need to pass in the literal type, of course. Okay. So if the guard is not present, it's null. We're just going to construct a true pattern. So from that, we can actually construct the condition of this if clause, which is going to be an AND expression of the pattern matcher and the guard. And we need to lower that because AND expressions unsurprisingly get lowered. Now I wonder, since AND expressions get lowered like this, we might just get away by not lowering the guard at all, because AND expressions will, because lowering the AND expressions will lower the two parts, so we don't need to do the work twice. Lowering once is enough. Well, it would lower once anyway, but it would traverse the tree unnecessarily twice. So I think that we want to do is collect these conditions and condition value pairs. So we also need to visit the value. And we might also not lower here because we will just call lowering on the whole thing at the end. So what we're going to do now is let me think for a moment. So we will collect each condition value pair, and then we can fold them into an if-else-if chain. So let's do that. Here we can add the pair of condition, and to that we assign arm.value. Okay, this took more for me to figure out than it should have, and finally we can fold these list of pairs into this else-if chain. This is the way we construct them, and I think that we need to start folding. I wonder if it matters which way we fold, actually. It does, because we need to start building this if-else chain from the left, but else-ifs obviously nest to the right. I wonder if there's a left fold, or sorry, right fold that we need here. So I think it's called accumulate or aggregates. Yes, there is, but I think that it does left to right. So in reverse, we're going to do a. Why does that? Oh, because that's It's a function with the side effects. Okay, that's fine. Now we can finally do an aggregate, and do we need a seed? We do not. We just need a. Yes, we do. We might need a seed, and that should always be the first arm. Well, assuming there's a first arm, I don't think we ever check for that currently. Yeah, we definitely do need a seed, which is going to be the first condition value pair. Well, no, it's going to be the last one, which is not the first one. That means that we're going to skip first one and so the seed is going to be the last if expression, which will have a then clause as the first pair's condition and value. Let's do something like, well, let's call it last pair because that's what they are. And let's just not care about the case where it might be empty. We will handle it later. And what if there is no well, what should be the else value? It could be a can be a unit for now. And the type that this gets evaluated to is going to be the match expressions type. What did we call it? Node. Okay, and finally we can write the more interesting part, which is the accumulator function. And that's going to receive the the arm on the left and the accumulated expression on the right. So we're just going to construct an if expression, and on the left the arms condition and the arms value, and on the is it not called the, or is it parameterized the other way? I don't remember, I keep forgetting. Yes, okay, sorry. So what we're going to do is take the arms condition and its value, and on the else we're just going to pass in the accumulator. This is how we fold it essentially the right way. Okay, and this is going to construct us a bound if expression. We're just going to call it an if chain. And we're going to lower it I don't think that we want to lower the matched value either. We might do, I don't know. We'll skip it for now. We don't need to really match the first one. And this isn't what we're going to return. This is going to be the, well, this is this portion, but we need to wrap this in a block where we actually do the assignment to the temporary. So yeah, let's keep the lowered matched value actually, and let's construct the block here. So let's just call accept on this directly and do something like this. I don't remember how we construct a block. It's block expression. And we need locals. And I believe that we can just pass in the temporary. Although that might not be present, so I think we have examples of the other. Okay. We do something like this. I see. Okay. This is essentially what we need. So if there was no temporary because it didn't need to be stored, then we can just pass in an empty list. Otherwise, we're just going to pass in that single temporary. So as for statements, we're going to have two statements. And the value, well, we're actually just going to have one statement, and this is going to be the value, this if chain. And the value is going to be, well, let's cast this into a bound expression before I forget. And the singular statement we're going to have is actually the temporary's assignment, to actually assign the value to that statement, to the local symbol. Okay. Let's see. Okay, we don't construct patterns for matching yet, which is fine. We're going to have a switch for that. Oh, goofed up the syntax for switch expressions. And we're going to have a case for literal patterns. And we're going to have one for discard patterns. And we should fail here in these methods. Okay, and well, literal patterns are a bit harder, but the discard pattern is pretty trivial because this is just going to be a true. So a discard pattern always matches, so this one is pretty easy. And as for literals, we actually need to have equality. And I wonder if we have this in the well-known types. We don't. So every object has an equals method. Or like even to string, and as you can see it's there. Now let's navigate to well-known types and resolve that. To string is being resolved here. And I'm just going to create one for equals. That one, because we have two equals methods defined there. One's an actual member function or instance member function, but the static one, this should only match the static one, which we're intending to use. So let's use this in the rewrite process to construct the pattern. And what we're going to do is take n matches expression and turn it into, I could even have the comment here that discard matches expression gets turned into true. And here n matches expression turns into object dot equals n expression. We can just use an arrow function here as well. And we're going to construct a call expression. A receiver is going to be null. The method that we're calling is going to be object equals, and the arguments are going to be we're going to have two arguments. First is that we're going to extract the literal from the pattern. And the second one is going to be the actual matched value. And that should be it. Let's see. Okay, we're getting a not implemented exception in metadata codegen. And this is because we have unit passed in here in the encode signature type. Who is passing that in for us? going to be a box instruction, and it's trying to box the unit value as a string, which is interesting. Let's try to look at the generated IR code and see what's happening here. We might not have IR set up properly with the references, but that's easy to solve. So let's look at the IR. So what we have here is assigning 1 to num and then matching that with 4 arms. So box is 0 as an object. We store 1 into location 0, which is actually our num variable. It's being commented here. And then we load location 0, which is 1. We box both of them, which is fine so far. And then we're going to call system.object.equals, which is correct with the boxed values. And this seems to be correct for me. And if it's true, we're jumping to label 2, otherwise we jump to label 3. On label true, we just set location 1 to true and jump to label 4. Okay, this looks like an AND expression being compiled here. So label 4. Jump to label 6, where we store 0, and then we jump to label 32. Oh wow, this is a pretty hairy method. So I wonder where we are trying to box a unitary value. Let me copy this out and try to do some string searching to find it out. Okay, it's here in the as expression. Oh, I see. It's because the last branch we made it return unit, and it's trying to box it as a string. Huh. And this is causing the error. I wonder what if we just do a null literal. So when we lower it, the last if here, we could do something like instead of a bound unit expression, we will do something like a literal expression, and we use the factory version of the local one. Which is the bound tree factory. When we pass a null, maybe we want to construct a default value here. I'm not sure. At least not sure for now what we want to do here in the as branch, or if we even want to have an as branch here. And the type of it should be the node.type required. I don't remember what the codegen does here, to be honest. It doesn't seem to die on the IR level. It was a label 28, so we're storing null. Okay, that seems to be correct here. Obviously it would be a different matter for value types, but we will deal with that eventually. It's not important in terms of the feature, at least not for now. So what we could do is try to compile and see what the codegen does. It reused the window, so we can't really see anything here. Okay, so it doesn't do anything on null. Let's try to make it do something on null. I wonder how we can do null in the instruction encoder. Maybe if you use default here, I don't know. No, it won't like default. What if I use token 0 here? I don't know what that is. But we can definitely see. So this is compiling here, and the output should be into the same folder. Okay, and I'm going to open ILSpy in just a second on another screen. And I'll bring it into view in just a second. I'm also going to open up the DLL. Okay, let's take a look. It's pretty funky code, as you can see, being generated. Okay, it's a stack underflow, the else branch, so that's not good. So it believes it's a string. Oh yeah, because obviously we are assigning the string there. I just don't know how you would encode pushing and null. Oh, what if it's constant? I have no idea. I mean, technically ate it. I'm not sure if that's probably not valid IL. I wonder if it actually runs. Well, we're never going to hit that branch, but I wonder if the runtime will execute it. Oops, we cannot specify the output when we run. Okay, it executed fine. At least something ran, I don't know what did. We could do something like write out the result. Okay, so we got 1. That's good. Let's do 7. That should be a small number. Okay. And let's do something like 73. And that should be a warning big number or something. Okay. Yeah, because we print here and then we interpolate the actual number that we got. Alright, that should be the basic feature covered. So I am going to place a to-do here because that's probably not correct. And let's see the rest. The rewriting process is fine, I believe. And yeah, that's it. So what we did today is from syntax we went to let me open up my notes here. So from just having this parsed, we did type checking, and then we did the lowering to actually rewrite it into this uglier form that we can actually generate code for easier. Now there's a bunch of things that we have left out. We have not touched flow analysis, we haven't handled match expressions with zero arms, and we also probably have a codegen bug, as you could have seen, but those are things that we can play with off stream. Now what I'm planning to do is in some follow-up streams we're going to create tooling support, which is just going to be some syntax highlighting and see if the language server actually will like the new construct. We will also start thinking about ways to make this match more efficient with some tree construction algorithm that Roslyn does, for example, that can also help us with exhaustiveness checking. Let's do a couple more tests, I suppose. We could do something like check if we actually have found the common type for these. Let's see. I think they should find it as object, no? Oh, awesome, good. So it's telling me that there's no common type for int and string, which is fine. We can live with that, totally. I think that should be it. If we would actually want to be able to have it figure out that the common type should be object, then we should just mention object somewhere, like cast this integer to an object. Now we cannot do that because we don't have a cast syntax, but if we have something like m of object, sorry, and we mention it here, for example, then it should be fine. No common type, okay. Well, maybe we haven't done base types for primitives yet. I would have to check that out. Maybe integers do not count as object, or we do not allow value types to be converted implicitly to ref types. I don't remember. Okay, but it's nice to know that type checking actually works for match expressions, and it at least makes sure that you return one kind of value. Now, one last thing we can do is get rid of all these ugly squigglies. I could no, we don't save that file. What I can do is recompile the language server quickly. I think I have the compiler open here. Yep. And we have scripts for installing the language server, also the debug adapter and a bunch of other things. Now that we have it reinstalled, if I open up the project again, we shouldn't have any problems, and we should have actual live feedback from the compiler. It's telling me that there's no common type for them. If I undo it, it can figure out that it's a string. If I change every one of those, it will figure out that it's an int. So type checking seems to work. I cannot really test the pattern side because we only have integer patterns for now. Now, I think that should be it for now. Again, I'm planning the next stream to be about cleaning this up somehow and give some tooling support and give you guys an update on how I solved the to-dos and the open things that we have left. For the next few minutes, I'll stay on stream, and if there are any questions, please ask them now. Okay, I see no questions. I'm really happy that the stream was clear. I'll upload the recording eventually to the usual place. And thank you everyone for watching, and I'll see you guys next time. Bye bye.